Welcome to Boring Lectures, a scientific sleep aid. We know sleep doesn't always come easily. That's why we've created something deliberately and delightfully dull. Each episode, we take genuinely interesting scientific topics and present them in the most methodically detailed, soothingly repetitive way possible, designed specifically to lull you into peaceful sleep. Tonight, for our very first episode, we're diving deep into a topic so mundane that you'll be drifting off before you know it. So get comfortable, close your eyes, let go of the day, and prepare yourself for tonight's journey into the delightfully tedious world of mineral classification. We hope you're bored to sleep. To understand mineral classification, we must first understand what a mineral actually is. This might seem simple, but minerals have very specific characteristics that make them distinct from other natural substances. A mineral is defined by 4 key characteristics. First, a mineral must be naturally occurring. This means it must form in nature without human intervention. So while scientists can create mineral-like substances in laboratories, these are not considered true minerals. Second, a mineral must be inorganic. This means it does not come from living organisms or contain organic compounds. So even though certain shells and bones contain mineral-like material, the biological tissues themselves are not minerals. Third, a mineral must be solid. This requirement eliminates liquids and gases from being classified as minerals, no matter how much they might resemble minerals in other ways. And fourth, and this is perhaps the most important characteristic, a mineral must have a crystalline structure. This means that the atoms within the mineral are arranged in a highly organized, repeating, 3-dimensional pattern. This crystalline structure is fundamental to everything we'll be discussing today, so please keep this concept close to your mind as we continue. A mineral also has a specific chemical composition. This means that a particular mineral always contains the same types of elements in roughly the same proportions. For example, the mineral quartz always consists of silicon and oxygen in a specific ratio. If the composition changes significantly, it may no longer be considered the same mineral. Now, let's consider how many different minerals actually exist on Earth. Scientists have identified and cataloged over 3,500 different mineral species. That's right, more than 3,500 distinct types of minerals. And yet, despite this seemingly enormous number, mineralogists have developed elegant systems to organize all of them into manageable categories. These classification systems are the subject of our exploration today. Before we move on to those classification systems, let me take a moment to emphasize the importance of the crystalline structure. The atoms in a mineral are not randomly arranged. Instead, they're positioned according to very specific rules. Think of it like a vast, 3-dimensional checkerboard that extends infinitely in all directions, with atoms sitting at precise positions within this grid. The smallest repeating unit of this grid is called the unit cell. And the mathematical framework underlying all these unit cells is what we call the crystal system. This brings us naturally to our next section, the overall classification of minerals by chemical composition. Now that we understand what a mineral is, let's explore how mineralogists organize thousands of these minerals into coherent groups. There are actually 2 major classification systems in use today, and both are widely respected in the scientific community. The first system is known as the Dana classification system. It was developed way back in 1848 by Professor James Dana of Yale University. This system is primarily used in English-speaking countries, particularly in the United States. The Dana system divides all minerals into 8 basic classes, based primarily on their chemical composition. And this is worth noting, 8 classes to encompass over 3,500 minerals. Let's go through these 8 classes slowly and methodically. The first class is native elements. These are minerals that occur as single pure elements in their natural state, not combined with other elements. About 20 different elements can be found in this native state, and they are not particularly abundant in the Earth's crust. Examples include gold, silver, copper, platinum, and diamond, which is pure carbon. The second class is silicates. This is by far the largest group of minerals. In fact, silicates make up more minerals than all the other mineral classes combined. Silicates are made from metals combined with silicon and oxygen. Because of their abundance and importance, we'll be revisiting silicates in much greater detail shortly. But for now, just understand that this is the dominant class. Minerals like quartz, feldspars, and micas all belong to this class. The third class is oxides and hydroxides. These minerals are formed when metals combine with oxygen or with the hydroxyl group. They range from dull ores like bauxite to beautiful gemstones like rubies and sapphires. Corundum, magnetite, and hematite all belong in this class. The fourth class is sulfides and sulfosalts. These minerals are formed by combinations of metals or nonmetals with sulfur. They also include arsenides, antimonides, selenides, and tellurides. Most minerals in this group are opaque and quite heavy. Examples include pyrite and galena, which is an important iron ore. The fifth class is halides. These minerals are formed from halogen elements such as fluorine, chlorine, bromine, and iodine, combined with metallications like sodium, potassium, calcium, and magnesium. They tend to be relatively soft, and many are soluble in water. Common examples include halite, which is table salt, and fluorite. The sixth class is carbonates and borates. In carbonates, carbon and oxygen combine with metals to form carbonate groups. Calcite is a classic example. Borates are similar compounds, but formed with boron instead of carbon. Both tend to have relatively low hardness. The seventh class is sulfates, chromates, molybdates, and tungstates. These minerals are formed when sulfur or similar elements combine with oxygen and metals. They tend to be soft and translucent. Gypsum and barite are well-known examples from this class. The eighth and final class in the Dana system is phosphates, vanidates, and arsenates. These minerals are formed when phosphorus or similar elements combine with oxygen and metals. Apatite is a famous example from this group. Now, there is also a second major classification system in use today. It's called the Nickel-Strunz classification system, named after German mineralogist Carl Hugo Strunz, who developed it in 1941. This system is officially used by the International Mineralogical Association. The Nickel-Strunz system actually divides minerals into 10 classes instead of 8. These 10 classes are very similar to the Dana classes, but with a few additions and reorganizations. The Nickel-Strunz system includes the same basic 8 classes, but it separates native elements into their own distinct class, and it adds a 10th class for organic compounds. So the 10 classes in the Nickel-Strunz system are native elements, sulfides and sulfosalts, halides, oxides and hydroxides, carbonates and nitrates, borates, sulfates and chromates and molybdates and tungstates, phosphates and vanidates and arsenates, silicates, and finally organic compounds. Both systems serve the same basic purpose, to organize minerals by their primary chemical composition. And both systems recognize that silicates deserve special attention due to their overwhelming abundance. In fact, approximately 90% of the Earth's crust is made up of silicate minerals. This is why we'll spend considerable time exploring silicate structures in depth. But before we dive into silicates, we need to understand the fundamental geometric framework that underlies all minerals: the 7 crystal systems. The 7 crystal systems represent the 7 possible ways that atoms can be arranged in a repeating 3-dimensional pattern. These systems are based on the geometry of the unit cell, which is the smallest repeating unit of the crystal structure. Each crystal system is defined by the lengths of its three axes and the angles between those axes. The axes are typically labeled A, B, and C, and the angles between them are labeled alpha, beta, and gamma. Different combinations of axis lengths and angles create different crystal systems. Let's explore each of the 7 crystal systems in detail, starting with the most symmetrical and working our way to the least symmetrical. The cubic crystal system, also called the isometric system, is the most symmetrical of all crystal systems. In the cubic system, all 3 axes are of equal length, and all 3 angles between the axes are 90 degrees. This creates a perfectly symmetrical, cube-shaped unit cell. The high degree of symmetry in the cubic system means that crystals in this system look the same from multiple directions. This is why many cubic minerals form beautifully regular geometric shapes. Think of a perfect cube of pyrite, or the octahedral shape of a diamond crystal. Common minerals that crystallize in the cubic system include halite, which is common table salt. Halite typically forms perfect cubic crystals. Fluorite also crystallizes in the cubic system and often forms beautiful cubic or octahedral crystals. Garnet is another cubic mineral, typically forming 12-sided or 24-sided crystals due to the high symmetry of the system. Diamond and graphite are both forms of pure carbon, but diamond crystallizes in the cubic system, while graphite does not. This difference in crystal structure accounts for the vastly different properties of these 2 minerals. Diamond's cubic structure, with its strong covalent bonds in all directions, makes it the hardest natural substance. Graphite's layered structure, which we'll discuss later, makes it soft and slippery. Gold, silver, and copper also crystallize in the cubic system. These native metals form face-centered cubic structures, meaning that atoms are located not only at the corners of the cube, but also at the center of each face. This arrangement contributes to their malleability and ductility. The cubic system demonstrates how symmetry in the atomic arrangement leads to symmetry in the macroscopic crystal shape. It's a beautiful example of how the microscopic world directly determines what we can see with our own eyes. The tetragonal crystal system has slightly less symmetry than the cubic system. In the tetragonal system, 2 of the axes are equal in length, but the third axis is either longer or shorter. All 3 angles between the axes are still 90 degrees. So if you imagine taking a cube and stretching it along one direction, you would create a tetragonal unit cell. The tetragonal system creates crystals that often appear as elongated prisms with square cross-sections. These crystals have a single axis of higher symmetry, which is the axis that differs in length from the other 2. One of the most famous tetragonal minerals is zircon. Zircon typically forms short, 4-sided prisms terminated by pyramid shapes. Zircon is particularly interesting to geologists because it's extremely resistant to physical and chemical weathering, and it can be precisely dated using radiometric techniques. Some zircon crystals are over 4 billion years old, making them among the oldest materials on Earth. Cassiterite, which is tin oxide, also crystallizes in the tetragonal system. It typically forms short, dark-colored prisms. Rutile, which is titanium dioxide, is another important tetragonal mineral. Rutile often forms needle-like crystals and is commonly found as inclusions in other minerals, particularly quartz. Anatase and brookite are 2 other forms of titanium dioxide that also crystallize in the tetragonal system. The fact that the same chemical composition, titanium dioxide, can form 3 different minerals, rutile, anatase, and brookite, is an example of polymorphism. Each of these minerals has a different crystal structure and therefore different physical properties, even though they're chemically identical. The tetragonal system beautifully illustrates how a small change in symmetry, in this case making one axis different from the other 2, creates distinctly different crystal shapes and properties. The orthorhombic crystal system has even less symmetry than the tetragonal system. In the orthorhombic system, all three axes have different lengths. However, all three angles between the axes are still 90 degrees. So imagine taking a rectangular box where the length, width, and height are all different. That's the basic shape of an orthorhombic unit cell. Orthorhombic crystals often appear as prisms with rectangular cross-sections. They can be elongated along any one of the three axes, depending on the specific mineral and growth conditions. Many important minerals crystallize in the orthorhombic system. The olivine group, which includes forsterite and phyllosilicates, crystallizes in the orthorhombic system. Olivine is one of the most abundant minerals in the Earth's upper mantle. It's a silicate mineral, and we'll discuss its structure in more detail when we explore silicate classification. Topaz is another beautiful orthorhombic mineral. Topaz is an aluminum silicate that often forms well-developed prismatic crystals. It's prized as a gemstone and can occur in a variety of colors. Aragonite is the orthorhombic form of calcium carbonate. Remember that calcite is also calcium carbonate, but calcite crystallizes in the trigonal system. Aragonite and calcite are polymorphs, the same chemical composition with different crystal structures. Aragonite forms under higher pressure conditions than calcite, which is why it's found in certain geological environments and in the shells of many marine organisms. Sulfur, in its most common form, crystallizes in the orthorhombic system. Native sulfur typically forms yellow pyramidal crystals near volcanic vents and hot springs. Barite, which is barium sulfate, also crystallizes in the orthorhombic system. Barite often forms tabular crystals, meaning they're flat and plate-like, though it can also form other crystal habits. The orthorhombic system demonstrates how having three different axis lengths, while maintaining right angles between them, creates a wide variety of possible crystal shapes and mineral structures. The hexagonal crystal system is characterized by its six-fold symmetry. In the hexagonal system, four axes are used to describe the crystal structure. Three of these axes are of equal length and lie in the same plane, intersecting at angles of 120 degrees. The fourth axis is perpendicular to this plane and can be either longer or shorter than the other three. This four-axis description might seem complicated, but it accurately reflects the symmetry of hexagonal crystals. When you look down the main axis of a hexagonal crystal, you see a six-sided or hexagonal cross-section. One of the most important hexagonal minerals is quartz. Quartz is silicon dioxide, and it's one of the most abundant minerals on Earth's surface. Quartz crystals typically form six-sided prisms terminated by six-sided pyramids. The six-fold symmetry is clearly visible in well-formed quartz crystals. Beryl is another important hexagonal mineral. Beryl is a beryllium aluminum silicate, and it forms beautiful six-sided prismatic crystals. Different varieties of beryl, colored by different trace impurities, are known by different gemstone names. Emerald is green beryl, colored by chromium or vanadium. Aquamarine is blue beryl, colored by iron. Morganite is pink beryl, also colored by trace elements. Apatite is a hexagonal mineral that's important both geologically and biologically. Apatite is a calcium phosphate mineral that forms the mineral component of bones and teeth. In nature, apatite crystals often form hexagonal prisms. Graphite, which we mentioned earlier as a polymorph of diamond, crystallizes in the hexagonal system. In graphite, carbon atoms are arranged in flat hexagonal sheets. These sheets are held together by weak forces, which allows them to slide past each other easily. This is why graphite is soft and slippery, and why it's used as a lubricant and in pencils. Ice, which is frozen water, also has a hexagonal crystal structure. This hexagonal symmetry is why snowflakes have six-fold symmetry, with six branches or arms. Each snowflake is a single crystal of ice, and its six-fold symmetry directly reflects the hexagonal arrangement of water molecules in the ice crystal structure. The hexagonal system beautifully demonstrates how six-fold rotational symmetry in the atomic arrangement creates the characteristic hexagonal shapes we see in macroscopic crystals. The trigonal crystal system, also called the rhombohedral system, is closely related to the hexagonal system. In fact, some classification schemes treat trigonal as a subdivision of hexagonal. However, trigonal crystals have threefold symmetry rather than sixfold symmetry. Trigonal crystals can be described using the same four-axis system as hexagonal crystals, but they can also be described using three axes of equal length that intersect at equal angles, but not at 90 degrees. This creates a rhombohedral, or slanted cube-like unit cell. Calcite is perhaps the most important trigonal mineral. Calcite is calcium carbonate, and it's one of the most common minerals on Earth. Calcite forms the primary component of limestone and marble. Calcite crystals can take many different forms, but they all reflect the underlying trigonal symmetry. One of the most distinctive features of calcite is its perfect rhombohedral cleavage. When you break a piece of calcite, it tends to break along three directions, creating rhombohedral fragments. Corundum also crystallizes in the trigonal system. Corundum is aluminum oxide, and it's the second hardest natural mineral after diamond. Pure corundum is colorless, but trace impurities create beautiful colored varieties. Ruby is red corundum, colored by chromium. Sapphire can be any color of corundum other than red, with blue being the most famous, typically colored by iron and titanium. Quartz, which we discussed as a hexagonal mineral, is actually sometimes classified as trigonal, depending on which classification scheme is used. This is because quartz has elements of both threefold and sixfold symmetry. The technical distinction involves the precise arrangement of atoms, but for our purposes, it's enough to know that quartz can be considered either hexagonal or trigonal. Hematite is another important trigonal mineral. Hematite is iron oxide, and it's one of the main ores of iron. Hematite can appear metallic and silvery, or it can appear as dull, reddish-brown, earthy material. Despite variations in appearance, hematite always has a characteristic red streak. Tourmaline is a complex boron silicate that crystallizes in the trigonal system. Tourmaline forms elongated, three-sided prismatic crystals with triangular cross-sections. Tourmaline is notable for its range of colors, and individual crystals can even show multiple colors along their length. The trigonal system illustrates how threefold rotational symmetry, while less symmetrical than sixfold, still creates beautiful and distinctive crystal forms. The monoclinic crystal system has lower symmetry than the systems we've discussed so far. In the monoclinic system, all three axes have different lengths, similar to the orthorhombic system. However, only two of the angles are 90 degrees. The third angle, conventionally called beta, is not 90 degrees. This creates a slanted or skewed unit cell. The word monoclinic means one incline, referring to the fact that one axis is inclined relative to the other two. Many common minerals crystallize in the monoclinic system. The pyroxene group, which includes minerals like augite and diopside, crystallizes in the monoclinic system. Pyroxenes are important silicate minerals found in many igneous rocks. The amphibole group also crystallizes in the monoclinic system. Amphiboles include minerals like hornblende and tremolite. Amphiboles are similar to pyroxenes in some ways, but they have a different silicate structure, which we'll explore when we discuss silicate classification. Gypsum is a monoclinic mineral. Gypsum is hydrated calcium sulfate, meaning it contains water molecules in its crystal structure. Gypsum typically forms tabular or elongated crystals, though it can also form massive or fibrous aggregates. Gypsum is quite soft, with a hardness of only 2 on the Mohs scale. The mica group includes several monoclinic minerals. Muscovite and biotite are the most common micas. Micas are sheet silicates, meaning they have a layered structure. This layered structure gives micas their characteristic perfect cleavage in one direction. You can peel micas apart into extremely thin, flexible sheets. Orthoclase feldspar is a monoclinic mineral. Feldspars are the most abundant minerals in the Earth's crust, making up about 60% of it. Orthoclase is a potassium feldspar commonly found in granite and other igneous rocks. Azurite and malachite, two beautiful copper carbonate minerals, both crystallize in the monoclinic system. Azurite is a deep blue color, while malachite is a vibrant green. Both minerals form in the oxidized zones of copper ore deposits. The monoclinic system shows us how introducing one non-90-degree angle creates yet another distinct class of crystal structures with their own characteristic properties. The triclinic crystal system has the lowest symmetry of all the crystal systems. In the triclinic system, all three axes have different lengths, and none of the angles between the axes are 90 degrees. This means the unit cell is completely asymmetric, with no special geometric relationships between the axes. The word triclinic means three inclines, referring to the fact that all three axes are inclined relative to one another. Despite having the lowest symmetry, the triclinic system includes some important minerals. The plagioclase feldspar group crystallizes in the triclinic system. Plagioclase feldspars form a continuous series from albite, which is sodium feldspar, to anorthite, which is calcium feldspar. Plagioclase feldspars are extremely common in igneous rocks, particularly in basalt and gabbro. Microcline is a triclinic potassium feldspar. Microcline is very similar to orthoclase in chemical composition and properties, but it has triclinic symmetry rather than monoclinic. Microcline and orthoclase are polymorphs, forming under different temperature conditions. Turquoise, the blue-green copper aluminum phosphate mineral, crystallizes in the triclinic system. Turquoise rarely forms visible crystals, instead usually occurring as massive or microcrystalline material. But at the atomic level, its structure is triclinic. Kyanite, an aluminum silicate, also crystallizes in the triclinic system. Kyanite typically forms blade-shaped crystals and is notable for having different hardness in different directions. Along the length of the crystal, kyanite has a hardness of about 4 to 4.5. Across the width of the crystal, it has a hardness of 6 to 7. This variation in hardness is directly related to the arrangement of atoms in its triclinic structure. Rhodonite, a manganese silicate, crystallizes in the triclinic system. Rhodonite has a characteristic pink to red color and is sometimes used as a gemstone or ornamental stone. The triclinic system demonstrates that even with minimal symmetry, atoms can still arrange themselves into stable, repeating crystal structures. The lack of special angular relationships doesn't prevent the formation of beautiful and important minerals. And with that, we've completed our journey through all 7 crystal systems. From the highly symmetrical cubic system through to the asymmetric triclinic system, we've seen how different geometric arrangements of atoms create different classes of crystal structures. Each system has its own characteristic symmetry, its own characteristic crystal shapes, and its own set of minerals. Now let's turn our attention to silicate minerals. Remember that silicates make up approximately 90% of the Earth's crust. This dominance makes understanding silicate structures essential to understanding mineralogy as a whole. All silicate minerals are built around a fundamental structural unit, the silicon-oxygen tetrahedron. A tetrahedron is a geometric shape with 4 triangular faces. In a silicon-oxygen tetrahedron, a silicon atom sits at the center, and 4 oxygen atoms sit at the corners. The silicon atom forms strong covalent bonds with each of the 4 oxygen atoms. Now here's where it gets interesting. These silicon-oxygen tetrahedra can link together in different ways. Some tetrahedra exist as isolated units. Others link together in pairs, or in rings, or in chains, or in sheets, or in three-dimensional frameworks. The way these tetrahedra link together determines the type of silicate structure. Mineralogists classify silicate minerals into 6 major structural types based on how the tetrahedra are arranged. Let's explore each of these types in detail. The first type of silicate structure is the nesosilicate structure, also called orthosilicates or isolated tetrahedral silicates. In nesosilicates, the silicon-oxygen tetrahedra do not share any oxygen atoms with each other. Each tetrahedron exists as an independent unit, and metal cations bond the tetrahedra together. The olivine group is the most important family of nesosilicates. Olivine is a solid solution series between pure magnesium silicate called forsterite and pure iron silicate called phyllosilicates. In the crystal structure, isolated silicon-oxygen tetrahedra are bonded together by magnesium or iron cations. Olivine is extremely abundant in the Earth's mantle and is a major component of many igneous rocks. The garnet group also has the nesosilicate structure. Garnets have complex chemical compositions, but all share the same basic crystal structure of isolated tetrahedra. Different types of garnets contain different metal cations. Almandine contains iron and aluminum. Pyrope contains magnesium and aluminum. Grossular contains calcium and aluminum, and so on. Garnets crystallize in the cubic system and often form beautiful 12-sided or 24-sided crystals. Other important nesosilicates include zircon, which we discussed earlier as a tetragonal mineral, topaz, andalusite, kyanite, and sillimanite. These last 3 minerals are particularly interesting because they're all polymorphs of aluminum silicate. They have the same chemical composition, but different crystal structures and form under different temperature and pressure conditions. The second type of silicate structure is the sorosilicate structure, also called paired tetrahedral silicates. In sorosilicates, 2 silicon-oxygen tetrahedra share 1 oxygen atom, forming a pair. These paired units are then bonded together by metal cations. The epidote group minerals have the sorosilicate structure. Epidote is a complex calcium aluminum iron silicate that typically has a yellowish-green color. Epidote is common in metamorphic rocks. Lawsonite is another sorosilicate, a calcium aluminum silicate that forms in rocks that have been subjected to high pressure but relatively low temperature. These conditions occur in subduction zones where oceanic crust is pushed down into the mantle. The third type of silicate structure is the cyclosilicate structure, also called ring silicates. In cyclosilicates, the silicon-oxygen tetrahedra link together to form closed rings. The most common rings have 3, 4, or 6 tetrahedra, though other ring sizes can occur. Beryl is the most famous cyclosilicate. In beryl, 6 silicon-oxygen tetrahedra link together to form 6-membered rings. These rings are stacked on top of each other, creating channels that run through the crystal structure. Beryllium and aluminum cations occupy positions between the rings. The gem varieties of beryl, emerald, and aquamarine get their colors from trace impurities that occupy positions in this structure. Tourmaline is another important cyclosilicate. Tourmaline has an even more complex structure than beryl, with 6-membered rings of silicon-oxygen tetrahedra and a complex array of other elements, including boron, aluminum, and various other cations. The complexity of tourmaline's structure allows for the incorporation of many different elements, which is why tourmaline comes in such a wide variety of colors. The fourth type of silicate structure is the inosilicate structure, also called chain silicates. In inosilicates, the silicon-oxygen tetrahedra link together to form long chains. These chains can be single chains or double chains. Single-chain inosilicates include the pyroxene group. In pyroxenes, each tetrahedron shares 2 of its oxygen atoms with adjacent tetrahedra, creating a continuous chain. These chains run parallel to each other through the crystal, and metal cations occupy spaces between the chains. Common pyroxenes include enstatite, which is magnesium pyroxene, augite, which contains calcium, magnesium, and iron, and diopside, which is calcium magnesium pyroxene. Double-chain inosilicates include the amphibole group. In amphiboles, two single chains of tetrahedra join side by side, sharing additional oxygen atoms between them. This creates a wider, more complex chain structure. Like pyroxenes, metal cations occupy spaces between the chains. Common amphiboles include tremolite, actinolite, and hornblende. The chain structure of inosilicates has important implications for their physical properties. Pyroxenes and amphiboles both show cleavage parallel to the chains, but the cleavage angles are different. Pyroxenes have cleavage at angles of about 87 and 93 degrees, while amphiboles have cleavage at angles of about 56 and 124 degrees. This difference in cleavage angles is one way to distinguish these two mineral groups. The fifth type of silicate structure is the phyllosilicate structure, also called sheet silicates. In phyllosilicates, the silicon-oxygen tetrahedra link together to form continuous two-dimensional sheets. Each tetrahedron shares 3 of its 4 oxygen atoms with adjacent tetrahedra, creating a hexagonal network of tetrahedra that extends infinitely in 2 dimensions. The sheet structure of phyllosilicates gives these minerals their characteristic perfect cleavage in one direction. You can easily split phyllosilicates into thin sheets because the bonds between the sheets are much weaker than the bonds within the sheets. The mica group is the most important family of phyllosilicates. Muscovite is white mica, a potassium aluminum silicate. Biotite is black mica, containing potassium, magnesium, iron, and aluminum. Both muscovite and biotite can be split into extremely thin, flexible sheets. The clay minerals also have the phyllosilicate structure. Clays are fine-grained minerals that form from the weathering of other silicate minerals. Common clay minerals include kaolinite, illite, and montmorillonite. The sheet structure of clays and the small size of clay particles give clays their characteristic plastic behavior when wet. Chlorite is another common phyllosilicate, typically green in color. Chlorite is common in low-grade metamorphic rocks. Serpentine is a phyllosilicate that forms from the alteration of olivine and pyroxene in the presence of water. Serpentine often has a greasy or waxy luster and can form massive or fibrous aggregates. The sixth and final type of silicate structure is the tectosilicate structure, also called framework silicates. In tectosilicates, every silicon-oxygen tetrahedron shares all 4 of its oxygen atoms with adjacent tetrahedra. This creates a fully connected, 3-dimensional framework of silicon and oxygen atoms. If all the tetrahedra contain only silicon atoms, the result is quartz, silicon dioxide. Quartz has no cleavage because all the bonds in the structure are equally strong in all directions. When quartz breaks, it exhibits conchoidal fracture, creating smooth, curved surfaces. In many tectosilicates, some of the silicon atoms are replaced by aluminum atoms. When this happens, the framework develops a negative charge because aluminum has 1 fewer positive charge than silicon. This negative charge must be balanced by the incorporation of positive metal cations into spaces within the framework. The feldspar group minerals are tectosilicates with aluminum substituting for some of the silicon. Feldspars are the most abundant minerals in the Earth's crust. There are 2 main branches of the feldspar family: alkali feldspars, which contain potassium or sodium, and plagioclase feldspars, which form a series between sodium and calcium. Orthoclase and microcline are potassium feldspars. Albite is the sodium end member of the plagioclase series, while anorthite is the calcium end member. Between albite and anorthite, there's a complete solid solution series with varying proportions of sodium and calcium. The feldspathoid group also has the tectosilicate structure. Feldspathoids are similar to feldspars but contain less silicon. Nepheline and leucite are common feldspathoids. Zeolites are another important family of tectosilicates. Zeolites have very open framework structures with large spaces and channels. Water molecules and other small molecules, or ions, can move in and out of these spaces relatively easily. This property makes zeolites useful as molecular sieves and ion exchangers in various industrial applications. And with that, we've completed our tour through the 6 types of silicate structures, from isolated tetrahedra in nesosilicates, through paired tetrahedra in sorosilicates, rings in cyclosilicates, chains in inosilicates, sheets in phyllosilicates, to 3-dimensional frameworks in tectosilicates. We've seen how the versatile silicon-oxygen tetrahedron can link together in remarkably different ways to create the vast diversity of silicate minerals. Now let's explore how crystal structure relates to the physical properties of minerals. The arrangement of atoms in a crystal structure directly determines the mineral's observable characteristics. Understanding this relationship is fundamental to both identifying minerals and understanding why they behave the way they do. Let's start with hardness. Hardness is a mineral's resistance to scratching. It's determined by the strength of the chemical bonds in the crystal structure and by how closely the atoms are packed together. The MOA's hardness scale is the standard scale used to describe mineral hardness. It's a relative scale with 10 reference minerals, each representing a different hardness level. Let's go through them slowly. Hardness 1 is talc. Talc is so soft you can scratch it with your fingernail. Talc is a phyllosilicate with a sheet structure, and the weak bonds between the sheets make it extremely soft. Hardness 2 is gypsum. Gypsum can also be scratched with a fingernail. Gypsum is a sulfate mineral with a monoclinic structure. It contains water molecules in its crystal structure, which contributes to its softness. Hardness 3 is calcite. Calcite can be scratched with a copper coin. Calcite is a carbonate mineral with a trigonal structure. Hardness 4 is fluorite. Fluorite can be scratched with a steel knife. Fluorite is a halide mineral with a cubic structure. Hardness 5 is apatite. Apatite can just barely be scratched with a steel knife. Apatite is a phosphate mineral with a hexagonal structure. Hardness 6 is orthoclase feldspar. Orthoclase cannot be scratched with a steel knife, but it can scratch glass. Orthoclase is a tectosilicate with a monoclinic structure. Hardness 7 is quartz. Quartz easily scratches glass and is harder than most common materials. Quartz is a tectosilicate with a hexagonal or trigonal structure and very strong silicon-oxygen bonds throughout. Hardness 8 is topaz. Topaz is significantly harder than quartz. Topaz is a nesosilicate with an orthorhombic structure. Hardness 9 is corundum. Corundum is much harder than topaz. Corundum is aluminum oxide with a trigonal structure. The strong bonds between aluminum and oxygen atoms, combined with the compact crystal structure, make corundum extremely hard. Hardness 10 is diamond. Diamond is the hardest natural material. Diamond is pure carbon with a cubic structure. Every carbon atom is bonded to 4 other carbon atoms by extremely strong covalent bonds. These strong bonds in all directions make diamond exceptionally hard. Now let's consider cleavage. Cleavage is the tendency of a mineral to break along smooth, flat planes. Cleavage occurs when the bonds between atoms are weaker in some directions than in others. When the mineral breaks, it breaks preferentially along these planes of weakness. Minerals can have 1, 2, 3, 4, or 6 directions of cleavage, or no cleavage at all. The number and orientation of cleavage directions is directly related to the crystal structure. Micas have perfect cleavage in one direction. This is because micas are phyllosilicates with sheet structures. The bonds within the sheets are very strong, but the bonds between the sheets are much weaker. So micas split easily parallel to the sheets. Pyroxenes and amphiboles have good cleavage in 2 directions. This is because these minerals are inosilicates with chain structures. The cleavage occurs parallel to the chains. The difference in cleavage angles between pyroxenes and amphiboles reflects the difference between single-chain and double-chain structures. Calcite has perfect cleavage in 3 directions. The 3 cleavage directions are related to the trigonal symmetry of calcite's crystal structure. When you break calcite, it tends to form rhombohedral fragments bounded by 3 sets of cleavage planes. Fluorite has perfect cleavage in 4 directions. These 4 cleavage directions correspond to the faces of an octahedron. This octahedral cleavage is related to fluorite's cubic crystal structure. Halite has perfect cleavage in 3 directions at 90 degrees to each other. This cubic cleavage is directly related to halite's cubic crystal structure. When you break halite, it forms smaller and smaller cubes. Quartz has no cleavage. Instead, quartz exhibits conchoidal fracture. This is because quartz is a tectosilicate with strong bonds in all directions. There are no planes of weakness, so the mineral doesn't preferentially break in any particular direction. Fracture is how a mineral breaks when it doesn't break along cleavage planes. Conchoidal fracture, which we just mentioned with quartz, produces smooth, curved, shell-like surfaces. Many minerals with no cleavage or poor cleavage exhibit conchoidal fracture. Other types of fracture include uneven fracture, where the broken surface is rough and irregular, fibrous or splintery fracture, where the mineral breaks into fibers or splinters, and Hackley fracture, where the broken surface has sharp, jagged edges. Native metals often show Hackley fracture. Specific gravity is another important physical property. Specific gravity is the ratio of a mineral's density to the density of water. It's essentially a measure of how heavy a mineral feels compared to an equal volume of water. Specific gravity depends on 2 factors: the atomic weights of the elements in the mineral and how tightly the atoms are packed in the crystal structure. Minerals containing heavy elements like lead or gold have high specific gravity. Minerals with loosely packed structures have lower specific gravity. For example, quartz has a specific gravity of about 2.65. Calcite has a specific gravity of about 2.71. Baryte, which contains barium, has a specific gravity of about 4.5. Galena, which is lead sulfide, has a specific gravity of about 7.5. Gold has a specific gravity of about 19.3, making it one of the densest natural materials. Let's consider a few other important concepts related to crystal structure and properties. Isomorphism refers to minerals with similar crystal structures but different chemical compositions. When minerals can substitute for each other in a crystal structure, they're called isomorphic. For example, in the olivine series, magnesium and iron can substitute for each other, creating a continuous series from pure magnesium silicate to pure iron silicate. Polymorphism is a related concept where the same chemical composition can crystallize into different crystal structures under different conditions. The classic example is carbon. Diamond and graphite are both pure carbon, but with entirely different crystal structures and properties. Diamond forms under very high pressure, while graphite forms under lower pressure. Crystal habit refers to the characteristic shape that a mineral tends to form. For example, some minerals tend to form elongated prisms, while others form flat plates or equant cubes. Habit is influenced by both the crystal system and the conditions under which the mineral forms. Color in minerals can result from several factors. The inherent color of a mineral depends on the elements present and how they're arranged in the crystal structure. Some minerals are always the same color, while others come in multiple colors depending on trace impurities. For example, corundum can be ruby when it contains chromium impurities, or sapphire when it contains titanium impurities, or many other colors with different impurities. Luster refers to the way light reflects from the mineral's surface. Metallic luster means the mineral reflects light like a metal. Vitreous luster means it reflects light like glass. Other lusters include adamantine like a diamond, silky, pearly, and dull. Streak is the color of the mineral when it's finely ground into powder. Streak can be different from the color of the mineral in bulk because, as powder, different light scattering effects occur. For example, hematite can appear silvery or black in bulk, but has a red streak. As we approach the end of our journey through mineral classification and crystal structures, let's take a moment to appreciate the beautiful architecture of the system as a whole. At the highest level, mineralogists classify minerals by chemical composition. This gives us the 8 Dana classes, or the 10 Nickel-Strunz classes. Within these broad categories, minerals are organized by their crystal structure, the 7 crystal systems. But within the crystal systems, there's further organization. In silicates, for example, we have the 6 types of silicate structures: nesosilicates, sorosilicates, cyclosilicates, inosilicates, phyllosilicates, and tectosilicates. Within each of these, we have further subdivisions based on specific chemistry and crystal properties. And then there are the physical properties: hardness, cleavage, color, luster, density, optical properties. Each of these properties is intimately related to the underlying crystal structure. What emerges from all of this is a truly comprehensive, hierarchical classification system. Every mineral has its place. Every mineral fits into multiple categories simultaneously. It's in one of the chemical classes, in one of the 7 crystal systems, and if it's a silicate, in one of the silicate structural types. Its physical properties are predictable based on its structure. This is the profound beauty of mineral classification. It's not arbitrary. It's not a list of disconnected facts. It's a deeply interconnected system where structure determines properties, and understanding structure means understanding the mineral itself. For someone falling asleep, contemplating this beautiful architecture can be profoundly soothing. Everything has its place. Everything is organized. Everything makes sense. There are no loose ends, no unexplained mysteries within the system. Just perfect, logical order. Sleep well, knowing that the mineral world continues its eternal, orderly existence. Crystals growing slowly in perfect geometric patterns, atoms vibrating in their assigned positions within the crystal structures, maintaining the same organization they've maintained for millions of years.